Why did the Big Bang happen, and what was before it? Physicists do not really like to answer this question. However, a new theory by the Japanese physicist Kenji Hamada, known as renormalizable and background-free quantum gravity, gives its own answer. At the same time, the theory provides a new perspective on the physics of black holes, proposes a physical mechanism for the process known as the inflationary expansion of the universe, and also explains what the mysterious dark matter may turn out to be, and why, in fact, physicists have not yet been able to find it. Of course, the main interest of physicists in the new theory is explained by the fact that it claims to solve one of the major unsolved problems of modern physics. Why two perfectly functioning and repeatedly experimentally confirmed theories, quantum field theory and general relativity, refuse to work together? In our video today, we will of course examine what new theory was proposed by the Japanese physicist and how all these things are explained in it. But first, naturally, we will sort out what the essence of the problem with quantum gravity was, what possible solutions exist besides Hamada's theory, and of course, we will try to answer the question of how revolutionary this work really is for modern physics, and how, in general, one should regard all of this. A theory of gravity, any theory of gravity, must, roughly speaking, provide us with a formula that allows us to calculate the force with which a body will gravitationally attract other bodies, or more precisely, the gravitational field created by any object at a known distance from it. On macroscopic scales, general relativity, the theory of gravity by Einstein, copes with this task perfectly well. In it, the gravitational interaction is considered as a consequence of the curvature of spacetime by bodies possessing energy and momentum, in particular rest energy, that is, mass multiplied by the square of the speed of light. This component of energy dominates in most situations, but it is not the only one. For example, massless but energetic photons or other massless particles are also, with some caveats, able to create a gravitational field and participate in gravitational interactions. And here we smoothly move on to quantum gravity, whose task is to determine the magnitude of the gravitational interaction at quantum mechanical scales for atoms and subatomic particles at corresponding distances of the order of 10 to the power of minus 15 meters and smaller. And here it turns out that if we try to apply general relativity to such objects and at such distances, we face quite serious difficulties. Let me repeat, in general relativity, the gravitational field of a particle is determined by its energy and momentum. But in quantum physics, we cannot determine these quantities precisely. The uncertainty principle forbids us from knowing with ultimate precision certain pairs of quantities, such as the coordinate of a particle and its momentum, and therefore also its energy. The closer we are to the particle, the more precisely we fix its position, that is, its coordinate, and the less well-defined its energy and momentum become. As a result, the gravitational field also becomes blurred. At very small distances, it fluctuates so strongly that the pure gravity of the particle drowns in quantum foam. We can also approach this from another side. In quantum field theory, such fluctuations are interpreted as the birth and disappearance of virtual particles. These particles exist for an extremely short time, but they still distort the fundamental fields, including the gravitational field. At the same time, an observer at a distance r from the particle mainly feels those virtual particles whose wavelength is comparable to this distance. The smaller the distance, the shorter the wavelength, and therefore the more energetic the virtual particles that contribute. Their energy increasingly disturbs the field, and once again we come to the conclusion that the gravitational field of our original particle is lost against the background of the gravitational fields of virtual particles. The issue of accounting for quantum fluctuations is characteristic not only of quantum gravity, but also of the theories of all fundamental interactions, such as electromagnetism, the strong nuclear force, and the weak nuclear force. To solve it, quantum field theory invented an interesting trick known as renormalization. The basic quantum mechanical equations, for example, the one for the potential of the electric field of a charged particle, are left essentially unchanged, while the effects of quantum fluctuations are taken into account as contributions to the characteristic constants of interactions. In quantum electrodynamics, quantities such as the electron charge and the fine structure constant stop being true constants. More precisely, we say that at large distances from our particle, where quantum fluctuations do not play a defining role, these quantities are indeed constants. But at very small distances, they begin to change. For example, the effective electron charge, that is, the value fixed in experiment, increases as we approach the particle. It should be noted that this is not an actual physical increase of the electron charge or of the fine structure constant, but only a mathematical trick that allows us to effectively take into account the influence of quantum fluctuations. And in principle, one may try to use the same trick to construct a quantum theory of gravity by saying, for example, that at extremely small scales, that is, at extremely small distances from gravitating objects, the characteristic constants of gravitational interaction, such as the gravitational constant, will increase. A question arises: up to what limit will the constants increase under renormalization? The answer sounds rather bad. In theory, for both the electromagnetic field and the gravitational field, as the distance approaches zero, they will tend to infinity. But infinity is an unphysical quantity, and if when solving some problem you obtain infinity, it means that your theory is wrong. For quantum electrodynamics, however, one can, in practice, ignore this problem. Infinities appear only at extremely small distances of the order of 10 to the power of minus 290 meters. The so-called Planck length, which is considered the minimal spatial scale of applicability of all modern physics, is as large as 10 to the power of minus 35 meters. In simpler words, quantum electrodynamics breaks, beginning to produce infinities, only at scales where all of modern physics has long since ceased to work, and where the very notions of charge, mass, and the like lose their meaning. The most precise modern measurements allow us to work with distances no smaller than 10 to the power of minus 19 meters. This is about 10,000 times smaller than the radius of a proton, but about 1 trillion times larger than the Planck length. And at such distances, the measured electron charge increases by only about 3%. This is precisely why we say that quantum electrodynamics is a good, solid theory that can be successfully applied to solve all imaginable tasks. With quantum gravity, things are significantly worse. The gravitational constant tends to infinity, meaning that the gravitational contribution of a particle drowns in quantum fluctuations already at distant scales of the order of the Planck length. At larger scales, the renormalization of gravity more or less works. But the trouble is that at these very large distances, gravity, being the weakest of all four fundamental interactions, practically does not influence observable processes in the quantum world. In other words, quantum gravity that we can obtain by direct quantization and renormalization of general relativity turns out to resemble a crystal shard. When we try to use it to solve the very problems it should solve, it breaks, while for all other purposes, it is useless. Why does what works for electromagnetism not work for gravity? The simplest explanation is in terms of virtual particles. Indeed, only charged virtual particles contribute to the electromagnetic field. However, the law of conservation of electric charge requires that these particles be born only in pairs, a particle and its corresponding antiparticle with equal but opposite electric charge. That is why the total charge of the cloud of virtual particles must be strictly equal to zero. True, in space these particles are not distributed completely evenly. Virtual particles of the same sign as our real particle are, as it were, repelled from it, while particles of opposite sign are, as it were, attracted to it. This effect is called vacuum polarization. As a result, something like a dipole moment arises, which still makes its contribution to the resulting electromagnetic field. However, this contribution turns out to be rather weak, and what is even more important, it grows relatively slowly as the distance decreases. With gravity, everything is different. All particles that possess energy contribute to it, and the energies of particles and antiparticles do not cancel each other out, but are simply summed. Because of this, the role of quantum fluctuations in gravity grows more rapidly and in a much more dramatic way. Physicists say that general relativity turns out to be non-renormalizable, which means that it is impossible to build a quantum theory of gravity by quantization and renormalization from it. However, a renormalizable theory of gravity definitely must exist. Apparently, it is precisely such a theory that describes what happens inside black holes, and it also played an important role in the early universe during the very first moments of its existence. We cannot understand the processes there without such a theory. And finally, without a quantum theory of gravity, we cannot create the theory of everything, a universal physical law that would describe, with one single, though very complex formula, all physical processes in our universe. And physicists very much want to create such a theory. And it cannot be said that no such attempts have been made so far, or that those attempts were completely unsuccessful. For example, in the year 1976, one of the greatest physicists of the second half of the 20th century, the creator of the theory of unification of the electromagnetic and weak nuclear interactions, Steven Weinberg, proposed his own theory. It became known as asymptotically safe gravity, safe in the sense that it is not in danger of breaking down when approaching Planck scales. Weinberg reasoned very simply. If we quantize Einstein's equations, then quantum gravity breaks exactly where it should not break. Therefore, we need to modify Einstein's equations so that it no longer breaks. To be precise, Weinberg does not even change them very much. He simply says that, in accordance with the renormalization formalism, we replace in these equations the gravitational and cosmological constants with so-called running constants, which depend on the scale at which we study the system. Speaking specifically about the gravitational constant, at large scales, it tends toward a constant value of 6.7 times 10 to the power of minus 11 cubic meters per kilogram per second squared, which is what we observe in the macroscopic world. As the scales, that is, the sizes at which we study the system, decrease, it begins to grow, just as it should in a properly quantized theory of relativity. But unlike in that theory, it does not grow infinitely. Instead, it reaches a maximum fixed value several times greater than the tabulated value of the gravitational constant, precisely at the Planck scales. After that, it begins to decrease, so that at distances approaching zero, it itself tends to zero. One may say that in asymptotically safe gravity, starting from a certain scale, space reacts less and less to disturbances introduced by matter, whether by real particles or by virtual ones, until finally it disappears completely. This construction of the dependence of the gravitational constant on scale and distance allows asymptotically safe gravity to eliminate not only the infinities generated by quantization, virtual particles, but also the intrinsic infinities of general relativity observed when the distances between gravitating bodies decrease to zero. In other words, it also solves the problem of singularities, such as in black holes or in the primordial singularity of the Big Bang. The approach of asymptotically safe gravity, of course, rather strongly resembles fitting the solution to the answer. And to a large extent, it really is just that. In fact, there is nothing terrible in this. We are not at an exam. Essentially, the task of physics is precisely to find such a solution, that is, a theory, which will correspond to the answer, that is, to the observed and experimental data. Another matter is that in the case of asymptotically safe gravity, we are practically deprived of the possibility to check whether the solution corresponds to the answer in practice. If we could actually study gravity at Planck, near Planck, and sub-Planck scales, and verify that the gravitational constant indeed behaves as asymptotically safe gravity predicts, then we could say for certain whether Weinberg's hypothesis is correct or not. Alas, as I have already said, the Planck scales are very far from our present-day measurement capabilities. This means that we cannot test whether the universe is really arranged the way asymptotically safe gravity assumes, or whether the problem of ultraviolet divergences is solved in some other way. Fortunately, we do have alternative ways of solving it, that is, alternative theories of quantum gravity. For example, there exists the so-called theory of loop quantum gravity, whose key point is the assumption that the spacetime of our universe is itself discrete, as if quantized, divided into minimal cells with side length of the order of the Planck length. Within this theory, it is assumed that distances smaller than the Planck length have no physical meaning in our universe at all. In other words, this is an approach opposite to Weinberg's approach. There it is stated that quantum gravity at sub-Planck scales breaks down completely correctly, just as it should, because we are asking the theory to calculate something that from the very beginning has no meaning. All that remains is just one little thing to prove the existence of this very discreteness and granularity of space at the Planck scale, that is, at the order of 10 to the power of minus 35 meters. Unfortunately, for now, this also lies far beyond our capabilities. The third candidate for the role of quantum gravity belongs to a very broad and popular theory today, which is often, and not quite correctly, called string theory. This theory has its own way of fixing the equations of quantum gravity and avoiding ultraviolet divergences. Essentially, this method resembles the one used in loop gravity by introducing a kind of natural limitation on considering processes at scales smaller than the Planck length. But while in loop gravity this limitation is strict, that is, scales smaller than the Planck length are considered entirely non-physical, in string theory the limitation is softer. Let me remind you, string theory states that all observable particles, as well as unobservable virtual particles, are merely different modes of vibration of tiny strings, whose length, in most versions of string theory, is assumed to be approximately equal to the Planck length, that is, on the order of 10 to the power of minus 35 meters. And so, since the size of a string is the fundamentally minimal possible size of a particle, probing to deeper levels of smaller scales will not lead to the birth of new particles, but only to new modes of vibration of the very same strings that we already have. One may say that string theory solves the problem of infinities in a third way. It imposes a certain limit on the amplitude of quantum fluctuations, or equivalently, on the mass of the virtual particles that are created, and accordingly on their influence on gravity and therefore on spacetime. That is, unlike loop gravity, scales smaller than 10 to the power of minus 35 meters do not lose meaning, and unlike asymptotically safe gravity, string theory does not cease to work at those scales. Instead, the quantum infinities are suppressed thanks to the restrictions on the birth of virtual particles, while the intrinsic infinities of relativity are suppressed thanks to the fact that the strings themselves have a finite size and therefore cannot be brought arbitrarily close to zero distance. The problems of string gravity are similar to those of loop gravity. In both theories, certain physical objects are introduced. In loop gravity, space cells or cubes. In string theory, the strings themselves, whose existence is still only a hypothesis that must first be proven. And confirming or refuting the existence of strings and everything connected with them turns out to be no easier, and from some points of view even harder, than proving the discreteness of space in loop theory. And finally, the fourth candidate for the role of a quantum theory of gravity is the very renormalizable and background-free quantum gravity proposed by Hamada in the year 2025. In its approach to solving the problem, it is in some respects similar to Weinberg's asymptotically safe theory, while its results turn out to be closer to those predicted by string theory. Unlike loop gravity or string theory, Hamada does not introduce additional physical objects. Like Weinberg, he simply proposes a mathematical way of modifying the equations of relativity that allows us to avoid ultraviolet divergences, that is, the infinities that break physics. However, in a surprising way, Hamada's mathematical modification of Einstein's equations acquires physical meaning after the fact. I will not go too deeply into the mathematics of Hamada's theory, which is rather complex, noticeably more complex than even the already difficult mathematics of Weinberg's theory. Instead, I will try to use analogies that are appropriate in terms of the physical meaning. One may say that in Hamada's theory, space-time itself turns out to possess elasticity, which resists deformation under the influence of gravity, and the measure of resistance is proportional not to the first power of deformation. As a spring resists stretching according to Hooke's law, but to its square. At small deformations, this resistance is practically equal to zero. Space behaves just as in Einstein's general relativity, where it can be stretched in any way and to any extent. But at large deformations, that is, in very strong gravitational fields, an analog of elasticity appears, resisting further stretching and at a certain stage balancing it. Mathematically, this is expressed through the appearance on the left-hand side of Einstein's equation of additional terms proportional to the square of the scalar curvature of space and to the square of the Ricci tensor. This phenomenon eliminates both types of infinities in one stroke, both quantum and Einsteinian. Singularities with infinite density and infinite curvature of space, as in black holes and classical relativity, are impossible in Hamada's theory because the very elasticity of space will not allow them to form, resisting further growth of gravitational forces. Quantum fluctuations, that is, in our language, the foam of virtual particles, do indeed tend to stretch space, but starting from a certain stage, space simply refuses to stretch any further. In simpler words, Hamada began from the same starting point as Weinberg. He tried to find a mathematical trick that would eliminate ultraviolet divergences. However, unlike the theory of asymptotically safe gravity, where infinities disappear simply because we ordered them to disappear, Hamada's theory discovers a fully physical and rather elegant mechanism for their disappearance. Hamada's theory does not assume the introduction of new physical entities. Instead, it only refines the properties of an entity already known to us and certainly existing, namely space-time. Even this alone already makes Hamada's theory very interesting and intriguing, but its advantages are not limited to this. Like other theories of quantum gravity, Hamada's theory does not allow the existence of real physical singularities. Whether in the center of black holes or in the primordial singularity of the Big Bang, matter is compressed very strongly, but not to infinity, because further compression is balanced by the elasticity of spacetime. Among other things, this allows Hamada to make a suggestion about what the Big Bang actually was. According to Hamada's theory, the current cycle of expansion of the universe was preceded by a contraction during which matter became denser and denser, creating an ever stronger gravitational field and stretching the fabric of spacetime more and more. At a certain stage, the elasticity of spacetime must have balanced gravity, but due to inertia, the universe compressed a little further, stretching the elastic film of spacetime slightly more than it should have been stretched at equilibrium. When the contraction finally stopped, spacetime turned out to be overstretched, possessing excess elasticity, and it began to straighten. This is similar to how someone jumping on a trampoline first pushes it down, storing the energy of elastic deformation in the rubber of the trampoline, and then the trampoline releases the accumulated energy, straightening and simultaneously pushing the jumper upward. The evolution of the universe, in Hamada's view, looks similar. Alternating cycles of expansion, the jumper flying upward, and contraction, the jumper falling downward. We are now living in the cycle of expansion. Hamada is not the first to propose such a concept. However, his theory is, as far as I know, the first to provide a mechanism for the origin of a very characteristic phenomenon that supposedly took place at the very beginning of the current phase of expansion, the so-called cosmic inflation. The essence is the following. At the very beginning of its existence, the universe went through a short but violent epoch of rapid expansion, when, over a time on the order of 10 to the power of minus 32 seconds, its size increased by about 10 to the power of 26. Most astrophysicists and cosmologists are confident that our universe really did pass through an inflationary expansion, because this hypothesis is in excellent agreement with observational data. However, its mechanism has remained unclear. Hamada proposes such a mechanism. In our trampoline analogy, the epoch of inflationary expansion is the period of time when the trampoline of stretched spacetime just begins to straighten, rapidly pushing the jumper universe upward. And finally, one more bonus of Hamada's theory should be mentioned. It naturally and organically leads to the prediction of the existence of massive invisible particles, practically ideal candidates for the role of dark matter. Dark matter allows modern cosmology to remain consistent, but its nature still remains a mystery. In order to understand how certain particles appear in quantum theories, we must recall that in quantum mechanics and quantum field theory, any perturbations of fundamental fields are often conveniently described as quanta, that is, as particles. For example, a perturbation of the electromagnetic field is conveniently described in the form of photon particles. In fact, the most important task of any quantum theory of a fundamental interaction is to determine which particles correspond to perturbations of the field of that interaction, and what the parameters of those particles must be. In all theories of gravity, and Hamada's theory is no exception, there appears a massless, uncharged particle with spin equal to 2. the so-called graviton. But in the equations of Hamada's theory, there appears another type of excitation of gravitational fields: massive, uncharged particles with spin equal to 0, which Hamada called dark particles. Dark particles participate only in gravitational interaction, and therefore it is practically impossible to directly detect their existence at the quantum level. As we have already said, gravity is far too weak to affect atoms and subatomic particles at all scales of length and energy accessible to us. However, just as on cosmic scales, gravity, weak in itself, begins to play a decisive role because of its unlimited range, so also on those same cosmic scales, the mass of a huge number of dark particles, generated by perturbations of the gravitational field, begins to make a significant and objectively measurable contribution to gravity. In other words, they do exactly what dark matter is supposed to do. Thus, Hamada's renormalizable and background-free quantum gravity not only offers an original and rather elegant solution to the key problem of quantum gravity, but at the same time explains a number of other phenomena that have long interested physicists. In this sense, it is a very interesting and promising addition to the family of quantum gravity theories. Alas, like all other such theories, this one has a major and unpleasant drawback. At our current level of technological development, we cannot and will not be able for quite some time to test and confirm or refute its key principles. Therefore, for now, it remains only a hypothesis. And this, in fact, is the key problem of quantum gravity at the present moment. Theorists have done a large and fruitful amount of work in creating candidates for such theories, but experimentalists, with their task of testing these theories and determining which one really works in our universe, so far cannot cope. But they are actively working in this direction, and sooner or later, I am sure, their efforts will be crowned with success. Then we will finally understand how and by what laws gravity works in the beautiful and amazing quantum mechanical world of subatomic particles. In our next videos, I will certainly continue to introduce my esteemed viewers to the current problems of modern physics and to the solutions that science offers, both venerable and well-established ones, and new, breakthrough ones from the very forefront of modern science. That is all for today. Thank you all for your attention, and see you very soon in our next videos.